Have you ever wondered why your smartphone, despite being millions of times faster than the computers that went to the moon, still needs to be plugged into a wall every single night? We have conquered the atom and mapped the human genome, yet we are still struggling to bottle lightning efficiently. The story of the battery is not just a tale of chemistry and physics, but a saga of human ambition, geopolitical chess, and the quest for ultimate control over energy. It is a story that began with a flickering problem in the late 20th century and is now leading us toward a total transformation of human civilization. To understand where we are going, we must first look inside the humble black box that sits at the center of our world. If you were to cut open a standard lithium-ion battery, you would find something surprisingly simple, almost primitive. It consists of thin layers of metallic foil coated in a dark, grimy paste, rolled up like a jelly roll and soaked in a chemical liquid. There are no moving parts, no gears, and no clicking circuits inside these cells. Yet this unassuming design is what allows a sleek glass slab to hold the sum of human knowledge in your pocket. The contrast between the battery's simple physical structure and its monumental importance is one of the great ironies of the modern era. These compact cylinders and pouches quietly power everything from the hearing aids in an elderly man's ear to the sophisticated sensors on a Mars rover. They are the silent engines of the digital revolution, enabling a world where information is instant and distance is irrelevant. But for all their success, a haunting question remains at the center of the industry. Why, in an era of exponential growth in computing, has the fundamental technology of the battery changed so little over the last 30 years? The answer requires us to rewind the clock to the 1980s, an era where the dream of a portable world first met a hard physical wall. In those days, the first mobile phones were not the sleek accessories we know today, but heavy, cumbersome bricks. These early devices exposed a glaring flaw in our technological progress, as they required massive packs of nickel-cadmium batteries just to function for a few minutes. You could carry a phone, but you couldn't actually use it for long without finding a power outlet, making the word portable feel like a cruel joke. During this period, it became painfully clear that the bottleneck for human progress was no longer the speed of our processors, but the weight of our energy. We could build smaller chips and brighter screens, but we could not figure out how to pack more electrons into a smaller space without things getting dangerous. The existing battery technologies of the time were heavy, inefficient, and suffered from a frustrating phenomenon called the memory effect. If you didn't drain them completely before recharging, they would forget their full capacity, slowly dying before they were even truly used. The scientific breakthrough that would eventually change everything began in the laboratories of Exxon under the guidance of a chemist named Stanley Whittingham. In the mid-1970s, Whittingham discovered that he could use lithium, the lightest of all metals, to create a battery with unprecedented energy density. He realized that lithium's intense desire to shed its electrons made it the perfect candidate for storing power in a very small footprint. His first prototype was a revelation, proving that we could store far more energy than anyone had previously thought possible. However, nature does not give up its secrets without a fight, and Whittingham's early lithium batteries were notoriously unstable. Lithium is a highly reactive element, and when pushed to its limits, it had a terrifying tendency to catch fire or even explode without warning. The laboratory benches were often scorched by these early experiments, serving as a reminder of the volatile power they were trying to tame. This initial failure set the stage for a chain of innovations, proving that a single invention is rarely enough to change the world. The torch was then passed to John Goodenough, a brilliant physicist who realized that the problem lay in the materials used for the battery's positive terminal. In the year 1980, while working at the University of Oxford, Goodenough introduced a cathode made of cobalt oxide. This change was transformative as it allowed the battery to store significantly more ions while remaining structurally sound. By using a metal oxide, he created a framework that could hold lithium ions like a high-density parking garage, vastly increasing the capacity of the cell. Even with Goodenough's breakthrough, the battery still utilized metallic lithium, which posed a constant risk of short-circuiting and fire. The final piece of the puzzle was placed by Akira Yoshino, a Japanese researcher working for the Asahi Kasei Corporation. Yoshino made the radical decision to eliminate metallic lithium entirely, replacing it with a specialized carbon material that could soak up lithium ions like a sponge. This created a system where ions simply moved back and forth between two stable materials, solving the safety problem and making mass production finally feasible. With these three discoveries combined, the world was ready for a commercial explosion that would redefine the end of the 20th century. In the year 1991, the Sony Corporation launched the first commercial lithium-ion batteries to power their new handheld camcorders. This moment was the quiet beginning of a global earthquake, as it allowed electronics to shrink in size while growing in capability. Suddenly, the heavy bricks of the past were replaced by devices that could fit in a briefcase and later, in a pocket. This commercial foundation did much more than just improve our gadgets. It laid the groundwork for the eventual transition of the entire global transport system. Without the stability and density of the lithium-ion cell, the modern electric vehicle would be an impossibility, relegated to the realm of science fiction. The same technology that powered a Walkman in the 1990s eventually scaled up to power a Tesla, and later, massive grid-scale storage facilities. We are currently living in the house that Sony, Yoshino, Goodenough, and Whittingham built. To truly appreciate the genius of this technology, we must look at the dance of the ions that happens every time you plug in your phone. A lithium-ion battery consists of four primary components: the anode, the cathode, the electrolyte, and the separator. Think of the anode and cathode as two separate cities, and the lithium ions as the citizens who move between them. When you charge your phone, you are using electrical pressure to force these citizens to move from the cathode city over to the anode city. As the battery discharges while you use your device, the ions naturally want to flow back to their original home in the cathode, releasing energy as they move. The electrolyte acts as the highway that allows these ions to travel, while the thin separator acts as a border guard, preventing the two cities from touching and causing a short circuit. One of the most fascinating parts of this process is the formation of a protective layer on the anode called the saga layer. This microscopic shield is what allows a lithium-ion cell to survive thousands of cycles of charging and discharging without falling apart. However, the dominance of lithium-ion technology comes with a hidden cost that we are only now beginning to fully understand. The global industry is now worth hundreds of billions of dollars, but it relies on a supply chain that is both fragile and ethically complex. To build these batteries, we require massive amounts of lithium, nickel, and cobalt, minerals that are often buried in some of the most remote and politically unstable parts of the world. Our hunger for portable energy has created a new kind of gold rush, one that leaves a significant environmental footprint in its wake. The mining of lithium requires millions of gallons of water in arid regions, often depriving local communities of their most precious resource. Even more concerning is the reliance on cobalt, much of which is mined in the Democratic Republic of the Congo under conditions that are frequently hazardous and exploitative. This introduces a deep geopolitical vulnerability, as a handful of nations control the vast majority of the materials needed for the green energy transition. We have traded our dependence on foreign oil for a dependence on foreign minerals, a shift that is currently reshaping the balance of global power. Beyond the environmental and ethical concerns, there are inherent physical limits to how much energy a liquid-based battery can safely hold. While lithium-ion batteries are generally very safe when treated properly, they carry the constant risk of a phenomenon known as thermal runaway. If a battery is physically crushed, overheated, or has a manufacturing defect, the internal separator can fail, leading to an uncontrollable internal fire. Because the electrolyte is a flammable liquid, these fires are incredibly difficult to extinguish as the battery provides its own fuel and oxygen. This risk is the primary reason why airlines are so strict about carrying large batteries in checked luggage, and why emergency responders need special training for electric vehicle fires. The urgency to find a safer, more stable alternative is not just about performance, but about public safety in an increasingly electrified world. We are pushing the limits of what liquid chemistry can do, and the cracks are starting to show. This has triggered a global race to develop the next generation of energy storage, a successor that can move us beyond the limitations of the current era. The most promising contender for the throne of the battery world is the solid-state battery. As the name suggests, this technology seeks to replace the flammable liquid electrolyte with a solid, ceramic or polymer material. This single change would be a revolutionary leap forward, as a solid electrolyte is virtually impossible to ignite, even if the battery is punctured. By removing the fire risk, engineers can pack the cells much more tightly together, significantly increasing the energy density and the range of electric vehicles. Solid-state batteries also promise much faster charging times, potentially allowing an electric car to be refueled as quickly as a gasoline tank. Because the solid material is more durable, these batteries could last for decades, outliving the vehicles they power. Major global players like Toyota, Tesla, and startups like QuantumScape are currently pouring billions of dollars into solving the manufacturing challenges of this technology. If they succeed, the solid-state battery will be the final nail in the coffin for the internal combustion engine, offering a level of convenience and safety that liquid lithium-ion can never match. While solid-state technology targets the high-end market, another innovation is emerging to provide a solution for the masses: the sodium-ion battery. Sodium is essentially salt, one of the most abundant and inexpensive materials on the planet, found in every ocean in the world. By replacing expensive lithium with common sodium, manufacturers can produce batteries at a fraction of the current cost. While sodium-ion batteries are heavier and hold less energy than their lithium counterparts, they are perfect for applications where weight isn't the primary concern. Think about the massive batteries needed to store wind and solar energy for our cities. These stationary units don't need to be light or small. They just need to be cheap and reliable. Sodium-ion technology could democratize energy storage, allowing developing nations to build out renewable grids without the crushing expense of lithium. This represents a shift from a philosophy of performance at any cost to a philosophy of abundance and sustainability. It is a reminder that the best technology isn't always the most powerful one, but the one that is most accessible to everyone. Even within the existing lithium-ion family, a quieter revolution is already taking place with the rise of lithium iron phosphate, or LFP batteries. Unlike the high-performance batteries that use cobalt and nickel, LFP cells use iron, which is cheap, safe, and plentiful. These batteries are incredibly durable, often lasting for thousands of more cycles than standard cells, making them ideal for workhorse vehicles and entry-level electric cars. Companies like BYD and CATL in China have already scaled this production to massive levels, and Tesla has integrated them into many of its vehicles. The rise of LFP is a practical compromise that proves we don't always need a scientific miracle to make progress. By choosing materials that are easier to source and harder to burn, we are creating a more stable foundation for the global shift to electric power. LFP batteries are the unsung heroes of the current energy transition, providing the reliability and affordability needed to move electric cars from a luxury novelty to a mainstream reality. They represent the maturity of an industry that is learning to balance its ambitions with the realities of the physical world. If we look even further into the future, the material known as graphene appears as the ultimate wildcard in the energy game. Graphene is a single layer of carbon atoms arranged in a hexagonal lattice, and it possesses extraordinary electrical and thermal conductivity. In a laboratory setting, graphene-enhanced batteries can charge in seconds rather than hours, and show almost no degradation over time. They are lighter, stronger, and more efficient than anything we have ever produced, suggesting that another massive leap in technology is possible. However, moving graphene from the lab to the factory is one of the greatest engineering challenges of our time. It is currently difficult and expensive to produce high-quality graphene at the scale needed for the global battery market. But history shows us that what is considered a laboratory curiosity today often becomes the standard of tomorrow. If the commercialization of graphene succeeds, we will enter an era where energy is no longer a constraint on our movement or our imagination. It would be the final piece of the puzzle in creating a truly frictionless world. As we stand here in the middle of the 21st century, it is helpful to view the lithium-ion battery not as the ultimate destination, but as a crucial bridge. Just as the steam engine gave way to the internal combustion engine, the liquid cell battery is the precursor to something much greater. We are currently living through potentially the largest energy transformation since the discovery of electricity itself. The shift from burning ancient plants to storing solar and wind energy and advanced materials is a fundamental change in how our species interacts with the planet. This journey into the heart of the battery reveals a profound lesson about the nature of progress. Nothing is truly finished. Every solution we create introduces new challenges that force us to think deeper and innovate further. The struggle to improve energy storage is a mirror of the human condition, our constant desire to overcome the limits of time and space. We are learning that to power our future, we must respect the materials of the earth and the safety of our communities. If you enjoyed this deep dive into the silent power of the battery, please subscribe to the channel and turn on notifications so you never miss a journey into the hidden side of our world. Thank you for your time and your attention, and I look forward to seeing you in the next exploration.